You know those incredibly powerful AI models that seem to understand and generate text like magic?
Hmm.
The ones that can write stories, answer your questions, even generate computer code?
Yeah, they're amazing.
Well, imagine taking that monumental pre-trained intelligence and teaching it to be brilliant at your very specific tasks, adapting it precisely to, well, your world.
Ah.
Today, we are taking a deep dive into just that, fine-tuning large language models, or LLMs.
And our mission with this deep dive really is to give you a shortcut, a clear path to understanding what fine-tuning fundamentally is,
Right.
why it's become such a, well, revolutionary way to get powerful AI working directly for you.
Yeah.
We'll also look at the surprising challenges that often pop up along the way.
Always challenges.
Oh, yeah. And the incredibly clever techniques researchers are constantly developing to, overcome them.
That's our goal. We're going to unpack the real insights and maybe some surprising facts from the sources you've shared, making even the most intricate details clear and hopefully engaging. Get ready for some serious aha moments as we explore how these AI giants are tailored for precision. The foundation. Why fine-tuning is a game changer. So let's unpack this. When we talk about these incredibly capable AI models, whether it's for understanding text or recognizing images, they don't just magically appear, do they?
No, not at all. They start with something truly foundational, pre-training.
Retraining, okay.
That's right. The core idea is that LLMs and even models for computer vision, they don't start from a blank slate. They're first pre-trained on truly massive data sets.
Massive, how massive?
We're talking trillions of words potentially for language models,
Yeah.
or millions, even billions of images for computer vision. This initial colossal training phase is where they learn fundamental patterns.
Okay.
For language models, this means things like grammar, common facts, the intricate relationships between words. For image models, it's about learning general visual features, edges, textures, basic shapes.
Huh. I think of it like a student who has literally read every book in the world. They have this incredibly vast general knowledge, right?
Exactly.
They understand the language works, they know a ton of facts, but they haven't specialized in anything yet.
That's a perfect analogy. Pre-training is exactly like that. It equips the model with a broad, deep understanding before it even thinks about specializing in anything specific.
And the benefits of doing this huge upfront work, they must be significant.
Oh, immense.
Right.
It has absolutely revolutionized fields like natural language processing, NLP, and computer vision. It allows for the development of these powerful models that are highly adaptable to a wide range of downstream tasks.
So you don't need a brand new model for every single problem.
Precisely. Instead of needing a bespoke model every time, this initial training provides a strong foundation of learned features, and that saves immense amounts of time and computational resources compared to trying to train a specialized model from absolute zero.
Right, because training from scratch on that scale is prohibitively expensive for most people.
Exactly.
So when we talk about some of these famous pre-trained models, what are some examples that really illustrate how this works in practice?
Well, in the text world, BERT is a fantastic example. It really excels at understanding text context
How so?
because it was trained using techniques like masked language modeling, where it has to predict hidden words within sentences, and next sentence prediction, which helps it grasp relationships between sentences. It really understands context.
Okay, Bert, for understanding, what about generating text?
Then you have the GPT family, which is renowned for text generation. They were trained on causal language modeling, which basically means predicting the next word in a sequence.
Ah, so that's why they're so good at writing continuous flowing text.
That's the idea. It's perfect for generating coherent text.
And it's not just language, right? You
Yeah.
mentioned vision models, too. For images, there are models like ResNet.
Absolutely. ResNet, for instance, learned general image features like edges, textures, common shapes from a massive data set called ImageNet. So when you bring a new image to a pre-trained ResNet model, it already has this sophisticated internal representation of what makes up an image generally. And that's incredibly powerful when you want to adapt it to a new visual task, like, say, medical imaging.
So here's where it gets really interesting for me. Once you have this pre-trained giant packed with all that general knowledge, how do you make it specific to your unique problem, your specific data?
Yes,
That's where the magic of transfer learning comes in, right?
that's the key. Transfer learning is really the art of smart adaptation. Instead of starting from scratch for a new problem, you intelligently leverage the broad knowledge that model gained during pre-training.
The knowledge from reading all those books.
Exactly, and you transfer it to your new task. It's all about being efficient and effective, especially when you have, limited data for your specific problem.
Which is often the case in the real world. So what are the key components of this process? What are we actually talking about when we say transfer knowledge?
We're typically looking at three main components. First, you have the source domain.
Okay.
This is the original massive data set, and the task the model was initially pre-trained on, think general internet text for an LLM, or millions of diverse images like ImageNet.
Got it. The general knowledge base.
Second, there's your target domain. This is your new specific task where you want to apply the model. And critically, this domain often has limited labeled data.
Like classifying specific medical x-rays, maybe? Or generating code documentation for my company's specific software library?
Perfect examples. It could be anything specific like that. And finally, you have the pre-trained model itself, which is the foundational model you're starting with, already packed with that general intelligence.
Source, target, pre-trained model. Got it. So how do we actually transfer this knowledge? Are there different ways to go about it?
Yeah, there are two main approaches, and they're often combined depending on the scenario. The first is feature extraction.
Feature extraction.
In this approach, you use the pre-trained model as a fixed feature extractor. Its weights are frozen.
Frozen, meaning they don't change at all.
Exactly. They don't change during this phase. You essentially pass your new specific data through this frozen model to extract high-level sophisticated features that the model learned during pre-training. Then you take those extracted features and you train a new, simpler classifier, maybe just a logistic regression or a small neural network, on top of those features to solve your target task.
Okay. So to use our ImageNet example again, if you had that pre-trained ImageNet model and wanted to classify different types of flyers, you could freeze its weights, run your flower images through it to get these deep learned features about edges and textures and shapes.
Even though it never saw a flower specifically.
Right. And then just train a simple classifier on those features to tell a rose from a tulip. The pre-trained models learned features are still incredibly useful.
Precisely. That's feature extraction.
Yep.
And then there's fine-tuning, which is really the core focus of this deep dive.
Fine-tuning. This sounds more involved.
Yeah, it is. Slightly. With fine-tuning, you take the pre-trained model and you actually adjust its weights directly to adapt it to your target task.
So you're not keeping everything frozen, you're tweaking the original model.
Exactly. You might fine-tune the entire model, letting all the weights adjust a little bit. Or a common strategy is to only fine-tune some of its later, more task-specific layers, while maybe keeping the earlier, more general feature layers frozen.
Okay, so for LLMs, how does this fine-tuning work in practice? Give me an example.
Sure. Take a BERT model, pre-trained on general text. You could fine-tune it on a data set of customer reviews to predict sentiment, say positive or negative.
Right.
This might involve adding a new classification layer on top that learns specifically to map the BERT output to a sentiment label. But you also allow the BERT model's own internal weights to adjust slightly to better understand the specific nuances of sentiment as expressed in product reviews.
So it learns the language of reviews better.
Yeah. Exactly. Or, in the vision space, imagine fine-tuning a ResNet model on chest x-rays to detect pneumonia. You might freeze those early layers that learned basic visual features like lines and edges.
Because those are always useful.
Right. And you primarily fine-tune the later layers that need to learn to discern the subtle patterns specific to pneumonia in an x-ray image.
It sounds like the overall benefit of this entire approach, whether it's feature extraction or fine-tuning, is that you can achieve really high accuracy on your specific task.
Often state-of-the-art accuracy.
With significantly less task-specific data and way fewer computational resources compared to trying to train one of these giant models from scratch for your specific thing.
Absolutely. It truly is about being efficient and effective in your AI development. Leverage the giant's shoulders. 2, the roadblocks. Limitations and challenges in fine-tuning.
So we've talked about how amazing fine-tuning is, how it leverages these pre-trained giants to solve specific problems efficiently. It sounds almost too good to be true. Yeah. And as with anything powerful, it's not without its challenges, is it? There are some inherent limitations that pop up, even with the best pre-trained models.
That's a crucial point. While the pre-training paradigm has been revolutionary, it also introduces several limitations that you really need to consider when you move to fine-tuning. One of the primary ones is data bias.
Yes, the classic garbage in, garbage out problem, but amplified because the in is so massive for these models.
Precisely. Pre-trained models are, fundamentally, only as good as the data they are trained on. If that colossal training data is biased, or maybe unrepresentative of the specific target domain you're trying to fine-tune for,
Right.
the model will inevitably inherit those biases.
Hmm.
And sometimes it can even amplify them.
Can you give us an example of how this actually plays out? With an LLM, maybe?
Certainly. Imagine a language model that was pre-trained primarily on text from, say, a specific cultural context, let's say predominantly Western sources, just for example.
Okay.
When you later fine-tune or even just prompt that model with queries related to a non-Western context, it might exhibit biases towards the dominant culture it was trained on.
So it might generate stereotypes.
Exactly. It can manifest as generating stereotypical or even culturally insensitive content. Not because it's malicious, but simply because its vast general knowledge of the world is skewed by the dominant perspective in its initial training data.
And that leads to unfair, inaccurate, and potentially harmful outputs. A huge concern.
A major concern, especially for responsible AI deployment.
Okay, bias is one big issue.
Yeah.
And even though fine-tuning is more efficient than training from scratch, there's still a significant hurdle related to raw computational power, isn't there? The sheer computational cost.
Indeed. While it's a massive improvement over pre-training from scratch, fine-tuning large models, especially the really big LLMs we see today, can still demand significant computational resources.
We're talking lots of expensive hardware.
Yeah, powerful GPUs or TPUs, large amounts of memory, especially for the models with hundreds of billions of parameters. This can still be a substantial barrier to entry for, say, individual researchers or smaller organizations with limited budgets.
So it prevents them from fully leveraging these powerful models, even if they have a great use case.
It can, unfortunately. Access is still an issue.
Now let's talk about something called data distribution shift. This sounds a bit technical, but I gather it's a really critical challenge. It can really throw a wrench into fine-tuning performance, especially when models move from the lab into the messy, dynamic, real world. What exactly is it?
Data distribution shift is precisely what it sounds like. It occurs when the statistical properties of the model was trained on, whether that's the original pre-training data or maybe your initial fine-tuning data, start to differ from the data it encounters later on.
Later on, like during more fine-tuning or when it's actually deployed and seeing live data?
Exactly. Especially when it's deployed in the real world, which is constantly changing.
So like if you train a language model on social media posts from 5 years ago, but then people start using totally new slang, new memes, new ways of talking today.
Perfect analogy. The underlying characteristics of the language, the data distribution, have just fundamentally shifted.
And I understand there are specific types of these shifts.
Yes, it's helpful to distinguish them.
Okay.
First, we have covariate shift. This is when the input features themselves change, but the underlying relationship between the input and the output remains the same.
Okay, how would that look for an LLM fine-tuned on, say, product reviews?
Right. Imagine an LLM pre-trained on general internet text. Then you fine-tune it specifically for analyzing product reviews in a niche technical field, like maybe reviews for scientific equipment.
Okay.
You might encounter covariate shift because the input text, those product reviews, might use much more technical jargon, specific product names, or even unique acronyms that just weren't common in the broad pre-training data.
So the words are different, but maybe a positive review still uses generally positive language structures.
Exactly. The underlying task, say sentiment analysis, is this review positive or negative, might still work the same way logically for these new inputs. But the vocabulary or style of the inputs has shifted, making it harder for the model to apply its existing knowledge effectively.
Got it. Input changes, relationship stays the same. What's the other type?
Then there's label shift.
That's
This is a bit more nuanced. It occurs when the conditional distribution of input features given the target variable changes.
Okay, unpack that a bit.
In simpler terms, the relationship between what you see, the input features, the text, and what you're trying to predict, the label, like sentiment, actually shifts over time or context.
Okay, let's go back to the LLM fine-tuned for sentiment analysis on social media. How would label shift appear there?
Right. For sentiment analysis of social media posts, label shift could occur if, over time, sarcasm or irony becomes much more prevalent for expressing a certain sentiment.
So the words people use might not directly map to positive or negative sentiment the way they used to.
Precisely. A phrase that once clearly indicated positive sentiment might now commonly be used sarcastically to mean the opposite. The labels themselves haven't changed, positive, negative, neutral, but the way the input words relate to that sentiment has evolved. That's a crucial challenge for LLMs trying to understand these kinds of nuances.
And the consequences of this data distribution shift, whether it's covariate or label shift, sound pretty severe for LLM performance.
Well, they really are. It can lead to biased predictions where the model systematically skews its outcomes because the deployment data just doesn't match what it was trained or fine-tuned on.
Makes sense.
It can also cause overfitting, where the model perhaps memorizes the specific fine-tuning data it saw, but then performs terribly on new, unseen data for the shifted distribution.
Because it didn't learn the general patterns robustly enough.
Exactly. And crucially, it can cause calibration issues. This means the model's confidence scores, how sure it thinks it is about a prediction, no longer accurately reflect the true probabilities.
So it might be confidently wrong or wrongly unconfident. Neither is good.
Not at all. It leads to unreliable predictions you can't trust.
Okay, bias, cost, shift. And finally, there's a really nasty sounding problem, especially critical for LLMs that are supposed to retain broad knowledge. Catastrophic forgetting. This sounds like an AI memory wipe.
It's a pretty apt description, actually.
Yeah.
Catastrophic forgetting is a major challenge, particularly when you're fine-tuning LLMs sequentially on new tasks.
Sequentially, like fine-tune for task A, then later fine-tune that same model for task B.
Exactly. What happens is the model abruptly and drastically forgets previously learned information, and that includes its valuable, broad, pre-trained knowledge when it's learning something new.
Wow, it's like taking a master linguist who knows 10 languages, teaching them a new highly specialized 11th language, only for them to suddenly lose the ability to speak the first 10.
That's a great way to put it. Or like learning a new skill, maybe playing a new instrument, and suddenly losing the ability to perform an old, well-practiced one you've had for years.
That's not very robust or adaptable for an AI we want to use for multiple things.
Precisely. A model that loses its general understanding after specializing is severely limited in its utility. It makes it less robust and adaptable to new, unforeseen scenarios or tasks down the line. It's a fundamental problem in continual learning. 3. The ingenious solutions. Advanced fine-tuning and mitigation techniques.
So these challenges are pretty significant, right? We've got data bias, the computational cost, this tricky data distribution shift, and catastrophic forgetting, wiping out knowledge. It seems like a lot to overcome.
It definitely is a lot to tackle.
But this is where the ingenious solutions come in, the clever ways researchers are fighting back. And one of the biggest breakthroughs, particularly for these massive language models, is something called parameter efficient fine-tuning, or PEF.
Yes, PF.
The name itself, parameter efficient, suggests adapting smarter, not harder.
That's exactly the philosophy behind it. PEFT is really a groundbreaking approach, specifically designed to address both the computational cost and the catastrophic forgetting issues we just discussed, especially in the context of giant LLMs.
Okay, so what's the core principle? How does it work?
Its core principle is actually quite elegant. Instead of updating all the billions or even trillions of parameters in a large pre-trained model during fine-tuning.
Which is computationally brutal.
Exactly. Instead of doing that, PEFT methods modify only a tiny fraction of the existing parameters, or sometimes they introduce a very small number of new, trainable parameters, while the vast bulk of the original pre-trained model remains frozen.
Okay, so you're only touching a small part, leaving the giant foundation intact. That sounds incredibly efficient, especially for models with hundreds of billions of parameters.
It is. The practical advantages are really compelling, especially for LLMs.
Like what?
Well, first, significantly reduced computational cost. We're talking much less GPU or TPU time needed and much less memory. This makes fine-tuning these huge models much more accessible.
Lowering that barrier to entry we talked about.
Precisely. Second, lower storage requirements. Because you only need to store the small number of updated or new parameters for each task, not an entire copy of the fine-tuned multi-billion parameter model.
That's huge for managing different specialized versions.
Absolutely.
Yeah.
Third, a reduced risk of overfitting, especially when you have relatively small fine-tuning data sets, because you're not making drastic changes to the entire model structure.
Makes sense. Less freedom to just memorize the small data set.
Right. And finally, and this is crucial for LLMs, it offers a strong mitigation of catastrophic forgetting. Because most of the pre-trained parameters are preserved, the model is much better at retaining its general knowledge while still adapting to the new task.
Okay, so this sounds like a really big deal in the LLM world. What are some of the key PFT methods that researchers and practitioners are actually using right now?
There are several popular ones. One of the most widely used is probably LoRA, which stands for low-rank adaptation.
LoRA. Okay, how does that work?
The mechanism here is clever. LoRA freezes the original LLM weights, keeps them unchanged. Then, It introduces small, trainable, low-rank matrices that are designed to approximate the updates that would have been applied to the original weight matrices if you were doing full fine-tuning.
Okay. Low rank matrices. Approximating the updates.
Think of it like this. The change you want to make to a big matrix can often be represented efficiently by multiplying two much smaller, low-rank matrices together. LoRA trains only these small matrices. During inference, these trained low-rank matrices are then combined, usually added, to the original frozen weights to get the adapted behavior.
So instead of repainting a whole wall, updating the whole weight matrix, you just apply a very detailed decal, the low rank matrices, to quickly change its appearance in a targeted way.
That's a great analogy. It's targeted and much more efficient.
Can you give a real world example?
Sure. Let's say you want to fine-tune a large language model like Llama 2 for a very specific task, like generating marketing copy that matches a particular brand's voice and style.
Okay.
By applying LoRA, maybe specifically targeting the attention layers within the model, which are crucial for style and context, you can adapt Llama 2's output to align perfectly with that brand's voice. And you can do this without needing to retrain the entire gargantuan Llama 2 model. You just train the small LoRA matrices.
Wow, so you get customized performance without the massive cost. That's powerful. What else is in the PEFT toolkit?
We also have adapter layers, or sometimes just called adapters.
Adapters.
Here, the mechanism involves inserting small, task-specific neural networks into the existing pre-trained model's architecture. These adapters often have a bottleneck structure. They shrink the dimension down and then expand it back up to keep the parameter count low.
So you're slotting in little extra modules. Where do they go?
Typically, they might be placed after the attention mechanism or after the feed-forward networks within each transformer layer of the LLM. The key is that only these small adapter layers are trained during fine-tuning. The rest of the massive pre-trained model stays frozen.
And I remember reading their placement matters, something about serial versus selective.
Exactly. You can have a serial placement strategy where you might insert, say, two adapters per transformer layer, one after attention, one after feed-forward. So for a standard 12-layer BERT model, that would mean training 24 small adapter layers. Or for simpler tasks where maybe you don't need such deep adaptation, you might use selective placement. Here, adapters are only added in certain layers, maybe just the later ones, specifically to reduce the number of trainable parameters even further and potentially speed things up.
So you tailor the adapter strategy to the complexity of the task.
Precisely. More complex tasks might benefit from serial adapters throughout, while similar tasks like basic sentiment analysis might do just fine with selective placement in the upper layers.
Interesting. Okay, next up in the PEFT list was prefix tuning. How does that one work? That sounds like it adds something at the beginning.
It does. Prefix tuning introduces a sequence of trainable vectors. These are the prefixes to the beginning of the input sequence fed into the LLM's transformer layers. Or more accurately, these prefix vectors are added to the keys and values in the attention mechanism of each layer.
So it's like giving the model a hidden instruction or context at the start of each layer's processing.
That's a good way to think about it. These prefixes influence the subsequent computations within the model, guiding its behavior towards the target task, but without actually changing the original LLM parameters themselves. Only the prefix vectors are trained.
Okay, influencing each layer. And then there was prompt tuning, which sounds related, but maybe simpler.
It is, conceptually. Prompt tuning optimizes a single continuous prompt, which is essentially just a small trainable vector or sequence of vectors that is prepended directly to the input sequence itself before it even enters the first layer of the LLM.
So prefix tuning adds trainable stuff inside each layer's attention, while prompt tuning adds trainable stuff just once at the very input.
Exactly. This learned prompt then guides the pre-trained model's behavior for the specific task. While it's simpler and generally more memory efficient than prefix tuning, fewer parameters to train, it usually has a more limited contextual influence because it only modifies the initial input embeddings.
And I read its performance can be quite sensitive to the length of this learned prompt.
Yes, finding the optimal length for the prompt vector can be tricky and task-dependent. It's a trade-off between simplicity and influence.
Okay, so these PEFT methods, LoRA, adapters, prefix tuning, prompt tuning, are all about being smart and efficient with parameter updates, vital for the scale of modern LLMs and helps with cost and forgetting.
Definitely.
But what about battling those other big problems we discussed, like data distribution shift and also reinforcing the fight against catastrophic forgetting? What strategies exist there?
Right. Beyond PFT, we have a variety of other strategies, which we can often group into data-centric approaches and model-centric approaches.
Let's start with data-centric approaches. What can we do with the data itself?
Well, the first and perhaps most fundamental technique here is data augmentation. We touched on this briefly, but it's a core solution for robustness.
Right, creating more varied data. How does that work for text, specifically for LLM?
It involves artificially expanding your fine-tuning dataset by applying various transformations to your existing text samples. The goal is to expose the LLM to a wider range of linguistic variations, which helps reduce overfitting and makes it more robust to subtle shifts in language it might see later.
So what kind of transformations are we talking about?
Common techniques for text augmentation include back translation. This is where you translate a sentence to another language, say Spanish, and then translate it back to English. Often, the result is a slightly paraphrased but semantically similar sentence.
Ah, so easy to use and very reliable might become user-friendly and quite dependable.
Exactly. It generates natural-sounding variations. Other techniques involve synonym replacement, swapping words with their synonyms, or doing random insertion, deletion, or swapping of words to introduce minor variations in sentence structure or vocabulary carefully so you don't change the meaning too much.
Yeah.
And increasingly, people are even using paraphrasing with other LLMs. Yeah. You can prompt a powerful LLM to generate multiple different ways to phrase a question or state a fact, creating a very diverse set of inputs for fine-tuning your target model, especially useful for tasks like question answering.
So it's not just about having more data, it's about having more varied data. That seems crucial for LLMs dealing with the complexities and ambiguities of natural language.
Precisely. This kind of augmentation is vital, especially when you have limited data to begin with, like if you're fine-tuning an LLM on a very niche set of legal documents where examples of certain clauses are scarce.
Makes sense. What's another data-centric approach?
A very practical strategy, especially when dealing with data distribution shift, is simply fine-tuning on a mixed data set.
Mixed meaning.
Meaning, if you anticipate or have already observed that your data distribution is shifting, you can create a new fine-tuning dataset that combines your older pre-shift data with a smaller representative sample of your new post-shift data. Then you fine-tune the model on this mixture.
Ah, so you give it a bit of the old and a bit of the new.
Exactly. It helps the model adapt to the new distribution while hopefully retaining some of its knowledge about the old distribution, acting as a sort of bridge between the two.
Okay, those are data-centric. What about model-centric approaches for battling these issues, especially that nasty, catastrophic forgetting? What can we tweak in the model or the training process itself?
Here we look at techniques that modify how the model learns, or sometimes its architecture, beyond just PEFT. Standard regularization techniques are fundamental, even during fine-tuning.
Like L1 and L2.
Yes, L1, L2 regularization. These add a penalty term to the loss function that discourages the model's weights from becoming too large during fine-tuning. This prevents drastic parameter changes, which helps retain the pre-trained knowledge and also mitigates overfitting to the specific fine-tuning data.
Okay, keep the changes small. What else?
Dropout is another classic. It randomly sets some neurons, or their outputs, to 0 during each training step. This forces the model to learn more robust features that aren't overly reliant on any single part of the network. It builds redundancy.
Makes it less likely to collapse if one part gets overwritten later.
Kind of, yes. And batch normalization, while primarily used for stabilizing training, also has a regularizing effect. It normalizes the activations within each mini-batch. While these are general ML techniques, they become even more vital when fine-tuning massive LLMs, helping prevent catastrophic forgetting by promoting more stable and distributed learning.
And a simple but seemingly effective technique I've heard mentioned is early stopping. How does that fit in?
Absolutely. Early stopping is simple yet powerful. You monitor the model's performance not just on the training data, but on a separate validation set during the fine-tuning process.
The practice exam data.
Exactly. If the performance on that validation set stops improving, or worse, starts degrading, for a certain number of training epochs, we call that threshold, the patience, you just stop the training process right there.
Even if the training loss is still going down.
Yes, because that indicates the model is starting to overfit to the fine-tuning data and is losing its ability to generalize, which is often linked to forgetting broader knowledge. Early stopping prevents this overfitting and helps preserve generalization.
Smart. We can also just train multiple models, right? Like an ensemble.
Yes, ensemble methods. The idea is to train multiple models, maybe fine-tuned from the same pre-trained base, but with different random seeds. or using different subsets of the fine-tuning data, or even different PEFT methods, and then combine their predictions at inference time, maybe by averaging or voting.
How does that help with shift or forgetting?
It can significantly improve robustness to data distribution shift, because errors made by individual models might cancel each other out. The ensemble prediction is often more stable and less prone to the biases or overfitting of any single fine-tuned model. It also implicitly helps with forgetting, as different models might retain different aspects of the original knowledge.
Okay. Now, diving deeper specifically into catastrophic forgetting, are there particular model-centric strategies designed explicitly to prevent that AI memory wipe during sequential fine-tuning?
Yes, several really ingenious ones have been developed to help LLMs and neural networks in general remember past tasks while learning new ones. Two related ones are elastic weight consolidation, EWC, and synaptic intelligence, SI.
EWC and SI, what's the idea?
They are essentially smart regularization techniques. EWC tries to estimate how important each weight in the network was for performing well on previous tasks. It uses a concept from statistics called the Fisher Information Matrix to approximate this importance.
Okay.
Then, when training on a new task, EWC adds a penalty term to the loss function that specifically discourages large changes to those weights deemed important for the old tasks.
Ah, so it's like putting little protective locks on the crucial old memories, making them harder to overwrite.
That's a perfect analogy. SI is similar in spirit, but uses a different method to estimate weight importance, looking at how much each weight contributed to the change in the loss function during training on the previous task. Both aim to selectively protect important parameters.
Clever. What else? I think I've heard of replay methods.
Yes, experience replay is another major strategy. It's quite intuitive. The idea is to store a small subset of data samples from previous tasks in a replay buffer.
Like keeping some old flashcards.
Exactly. Then, when you're training the model on a new task, you don't just feed it data from the new task. You feed it a mix of the current task data and randomly sampled data from the replay buffer, the old flashcards.
So the model gets reminded of the old stuff while learning the new stuff.
Precisely. This constant rehearsal helps the model remember what it learned previously and prevents the new learning from completely erasing the old.
Simple but effective. Is there a more advanced version of that?
There is. Gradient episodic memory, GEM, is a more sophisticated replay method. It also uses a replay buffer, but instead of just mixing data, it explicitly looks at the gradients, the direction the model wants to update its weights.
Oh, cool.
GEM calculates the gradients for the current task and for the tasks stored in the replay buffer. It then projects the current task's gradient update in a way that ensures it doesn't increase the loss, i.e. worsen performance, on the previous tasks stored in memory.
Wow, so it actively prevents the new learning from directly interfering with the old knowledge mathematically.
Exactly. It's a more constrained and often more effective way to manage the trade-off between learning new things and remembering old ones.
This all sounds like a fantastic toolkit for handling the model itself and the data variations. But what if the biggest bottleneck isn't the model or the shift, but just the sheer cost or time involved in labeling the specific data you need for fine-tuning in the first place, especially for specialized tasks?
Yes, that's a very common, very practical challenge. And that's precisely where active learning comes in. It's all about smart data selection for labeling.
Smart selection, meaning you don't just label random data points.
Exactly. The core principle of active learning is this. Instead of randomly selecting data to be labeled by humans, you use the model itself to help you actively select the most informative, unlabeled data points.
Most informative. How do you define that?
Informative usually means the data points that the model is currently most uncertain about, or the ones that, if labeled, would likely lead to the biggest improvement in the model's performance. The goal is to maximize the model's accuracy with the minimum amount of human labeling effort.
Which is critical when human labeling is expensive, slow, or requires specialized expertise, like doctors labeling medical text or lawyers labeling legal documents for an LLM.
Absolutely. That's where active learning shines.
So how does it work? Is it a loop?
Yes, it's typically an iterative process, the active learning loop. You start by training an initial model on whatever small label data set you have. Then, you use this initial model to make predictions on a large pool of unlabeled data and estimate the model's uncertainty for each prediction.
Find the ones it's shaky on.
Exactly. Next, you select a batch of the data points where the model was most uncertain or deemed most informative, according to some strategy. You send only these selected points to your human annotators to get labels.
Saving them from labeling the easy stuff the model already knows.
Precisely. You then add these newly labeled informative data points to your training set, retrain the model, which should now be better, and then you repeat the cycle. Predict on remaining unlabeled data. Select the most uncertain, get labels, retrain.
Until you hit your performance target or run out of labeling budget.
Exactly. It's a much more efficient way to use your labeling resources.
So what are the actual strategies for selecting that data? How does the model tell us what's most informative or what it's uncertain about?
One of the most common families of strategies is uncertainty sampling. Here, you prioritize labeling data points where the model is least confident in its prediction.
How do you measure that confidence?
There are various metrics. You could use least confidence sampling, where you pick the points where the model's highest probability prediction is still relatively low, for g closest to a random guess, or margin sampling, where you select points where the difference between the probabilities of the top two predicted classes is very small, meaning the model is struggling to distinguish between them. Or entropy sampling, which measures the overall uncertainty across all possible classes. Higher entropy means more uncertainty.
Okay, so if I'm fine-tuning an LLM to classify customer support tickets into categories like billing, technical support, feature requests,
Yeah.
using uncertainty sampling, I'd prioritize getting human labels for those tickets where the model is least confident. Like maybe it gives billing a 55% probability and technical support a 45% probability. It's really unsure.
Exactly. Labeling those ambiguous cases helps the model learn the crucial distinctions between similar categories much faster than labeling random tickets it's already confident about.
Makes total sense. What's another strategy besides uncertainty?
Another popular one is query by committee, QBC.
Query by committee. Sounds democratic.
Kind of. It involves training not just one model, but a committee of multiple models. These models could be the same LLM architecture, but trained with different random initializations, or maybe on slightly different subsets of the initial labeled data, or even using different fine-tuning techniques.
Okay, you have a panel of slightly different expert models. Then what?
Then you have each model in the committee make a prediction on the unlabeled data points. You select the data points where the committee members disagree the most amongst themselves.
Ah, if the experts can't agree, that point must be really ambiguous or informative.
That's the intuition. If multiple diverse but capable models all struggle to classify a particular input consistently, that input is likely very valuable to learn from.
So if I'm fine-tuning an LLM for, say, medical diagnosis based on patient text descriptions, and I have a committee of 3 slightly different fine-tuned LLMs, and 2 say condition A, while one says condition B for a particular patient description, that description gets flagged for review by a human medical expert.
Precisely. It helps focus expert attention on the most contentious cases where the models collectively show uncertainty.
Very clever.
Oh.
Any other major active learning approaches?
One more technique worth mentioning, which relates back to uncertainty, is using Monte Carlo dropout, MC dropout, for uncertainty estimation.
Dropout again, but I thought that was for regularization during training.
It is, but a neat trick is that you can also apply dropout at test time or inference time. Normally, dropout is turned off then.
Okay. Why would you do that?
If you run the same input through the model multiple times, say 50 times, with dropout enabled each time, you'll get slightly different predictions each time because different neurons are randomly dropped out.
Right. The network is slightly different each run.
Exactly. You can then look at the variance or standard deviation of these 50 predictions. A high variance suggests the model is uncertain about that. That input, its prediction changes a lot depending on which neurons are active. A low variance suggests high confidence.
So MC dropout gives you a way to estimate model uncertainty, even with just a single trained model, by running it multiple times with randomness, and you can then use that uncertainty estimate for active learning selection.
Precisely. It's a computationally efficient way to approximate the uncertainty without needing a full committee of models.
Wow. It's really clear that the field is constantly innovating, not just on the models themselves, but on all these surrounding techniques to make fine-tuning more accessible, more robust, more data efficient, and ultimately more effective in the real world, especially as these models get larger and are deployed in more critical and sensitive applications. 4. Practicalities and considerations. Making it work. So we've covered the amazing potential of fine-tuning, the tricky challenges that inevitably arise, and a whole arsenal of brilliant solutions and advanced techniques. Now, let's get down to the brass tacks. the practicalities and considerations for actually making this work successfully in a real-world project.
Right, moving from theory to practice.
And honestly, it feels like the unsung hero of successful fine-tuning, maybe all of machine learning, is meticulous data preparation. You can have the best model and techniques, but if the data isn't right,
You absolutely cannot overstate the importance of data. It all starts here. The very first step in data preparation is data acquisition and curation. Getting the right data, and often enough of it, is paramount.
where does this data typically come from for fine-tuning LLMs?
It can come from many places. There are excellent public data sets available for common tasks. Things like CNN Daily Mail for text summarization, Squad for question answering, or the Stack for code generation. You might use APIs to pull in specific data, like AlphaVantage for financial news if you're fine-tuning for financial sentiment.
What if there isn't a nice public data set for your specific niche task?
Then you might need to get creative. Web scraping is common for gathering things like product reviews, news articles, or even recipes, though you always need to be mindful of ethical considerations, terms of service, and the need for extensive cleaning afterwards.
Right, scraped data can be messy. And what if even scraping doesn't yield enough, especially for very specialized LLM applications? Can we just create data?
Yes, absolutely. Synthetic data generation is becoming an increasingly powerful and necessary alternative when real data is scarce or too sensitive to obtain.
How do you synthesize text data for an LLM?
For LLMs, this could involve using other, maybe larger LLMs to generate diverse paraphrases of existing sentences or examples you already have. You could use templates or rules to generate structured text, or even create entire artificial dialogues if you're building a chatbot for a domain with little real conversation data.
So you bootstrap data creation?
Exactly. For more structured domains that might feed into an LLM, techniques like generative adversarial networks, GNNs, simulations, or rule-based generation can create artificial examples. Think about generating synthetic medical text snippets, fake network logs for anomaly detection, or simulated customer queries when real ones are hard to get due to privacy or just rarity.
Okay, so you've acquired or synthesized your raw data. The next critical step, especially with scraped or synthetic data, must be data cleaning. This is where you wrestle with the noise, the inconsistencies, the errors.
Absolutely essential.
Hmm.
And for LLMs dealing with messy natural language, this is particularly crucial. It involves several steps. First, handling missing values. What do you do with incomplete text samples or records with missing fields? You might need strategies to impute them, or maybe just decide to exclude those incomplete samples if they're unusable.
Right.
Then, correcting errors and inconsistencies. It's huge for text. It means standardizing abbreviations or terminology, for example, ensuring New York City, NYC, and NYC are treated consistently if needed. It means ensuring your labels are consistent. You don't want positive, and pos floating around as different sentiment labels. It also involves removing irrelevant elements that could confuse the LLM, like leftover HTML tags, maybe excessive emojis or punctuation, or specific user mentions if you're working with social media text and they aren't relevant to the task.
And getting rid of redundant information seems important too.
Precisely. Removing duplicates is vital so your LM isn't biased by seeing the exact same information over and over again. This includes removing both exact duplicates and potentially near duplicates.
Near duplicates, like slightly reworded versions of the same review.
Exactly. For text data, identifying near duplicates requires defining some similarity metric, like Jacquard similarity or embedding cosine similarity, to catch them. You don't want the model to overfit on minor variations of the same core content.
Okay.
And finally, data transformation and standardization. This might involve things like ensuring consistent text casing, the example, converting everything to lowercase, maybe removing certain punctuation if it's irrelevant to the task, or encoding any categorical metadata associated with the text, like document types or user segments, into a numerical format the model can actually use, like one-hot encoding. It's all about getting your data into a clean, consistent, usable format for the LLM.
Yeah, that's a lot of work before you even get to fine-tuning. After all that meticulous cleaning, how do we set up our precious data for robust model training and, crucially, evaluation? That's where data splitting strategies come in, right? Dividing it up.
This is absolutely fundamental for trustworthy results. You need to divide your meticulously cleaned data into 3 distinct, non-overlapping sets.
3 sets.
Okay. First, the training set. This is the largest portion, typically maybe 70–80% of your data, and it's used to actually teach the model the patterns related to your task during fine-tuning.
That's what the model learns from.
Second, the validation set, or development set. This is a smaller portion, maybe 10–15%. It's not used for training the model's weights directly, Instead, it's used during the training process to do things like tune hyperparameters like the learning rate and decide when to stop training, early stopping. Think of it as the practice exam the model takes periodically to see how well it's generalizing.
Got it. Practice exam and the last set.
The test set, this is also typically 10–15% of the data, and it is absolutely crucial that this set remains completely unseen by the model and by you during the entire training and hyperparameter tuning process. It's held out until the very end.
The final exam.
Exactly. Use the test set only once after you've finalized your model and hyperparameters to get an unbiased estimate of how well your final fine-tuned model is likely to perform on new, unseen data in the real world. You must resist the temptation to tweak things based on the test set results.
Keep it sacred. Now, are there different ways to actually do this splitting beyond just randomly shuffling and dividing?
Yes, the splitting strategy matters a lot depending on your data. For simple cases where data points are independent and identically distributed, i.e., simple random splitting, shuffling, then splitting, is often fine.
But for more complex LLM scenarios,
You often need more sophisticated methods. Stratified splitting is essential when you have an imbalanced data set, meaning some categories or labels are much rarer than others.
like fine-tuning an LLM to detect a rare type of toxic comment, or classify legal documents where only 1% belong to a critical contract type.
It's exactly. Stratified splitting ensures that each set, train, validation, test, has approximately the same proportion of each target class as the original data set. This prevents the disaster scenario where, say, your test set accidentally contains 0 examples of the rare class, making your model look perfectly accurate when it actually can't handle those critical rare cases at all.
That seems incredibly important for real-world reliability. What about data with time dependencies?
Right. For time series data, like if you're fine-tuning an LLM on evolving news articles to predict future trends, or on chat logs ordered by time, random splitting would be wrong. It would let the model see the future. You need time-based splitting. Typically, you train on data from an earlier time period, validate on a middle period, and test on the most recent period. This assesses the model's ability to generalize to future unseen data, which is usually the goal.
Makes sense. Any other special splitting cases?
Yes, group-based splitting, or group K-fold, is important when your data has inherent groups, and you want to generalize to new groups. For example, if you have multiple medical text reports per patient, or multiple support interactions from the same user, you need to ensure that all data points from the same group, same patient, same user, end up in the same split, all in train, or all in validation, or all in test.
Why is that?
Because if data from the same patient is in both your training and test sets, the model might just learn to recognize that specific patient's writing style or medical history, rather than learning the general pattern you care about. It allows the model to cheat and inflate its performance metrics without truly generalizing. Group splitting prevents this data leakage.
So many subtle ways things can go wrong if you don't split carefully. And what if, even after splitting, you realize your training set is just fundamentally imbalanced, like 99% negative sentiment examples and only 1% positive? How do you handle that during fine-tuning?
That's a very common challenge in real-world LLM applications, detecting rare events, classifying niche categories. There are several standard techniques for handling class imbalance directly in the training process.
Okay, what are they?
Resampling is one approach. You can either oversample the minority class, basically, duplicating examples from the rare class, or, more cleverly, using techniques like SMOD, synthetic minority oversampling technique, to generate new artificial minority class samples based on the existing ones.
Creating more positive examples in our sentiment case.
Exactly. Or you can undersample the majority class, randomly removing examples from the overrepresented class until the dataset is more balanced. This is simpler, but risks throwing away potentially useful data.
Right. Over or undersampling? What else?
Data augmentation, which we already discussed, can be specifically targeted at the minority class to create more varied examples of it. For instance, if you're detecting rare types of bugs in code comments, you'd apply augmentation primarily to the examples of those rare bug comments.
Use augmentation strategically for imbalance.
Yes. Another powerful technique is cost-sensitive learning. Here, you modify the model's loss function to assign a higher cost to misclassifying examples from the minority class.
So the model learns that making a mistake on a rare positive case is much worse than making a mistake on a common negative case.
Precisely. It forces the model to pay more attention to getting the rare class right, even if it means slightly lower overall accuracy. The F1 score often improves significantly with this.
And finally, ensembles again.
Yes, ensemble methods can also help with imbalance. You could, for example, train multiple models, each on a different undersampled subset of the majority class, combined with all of the minority class data, a technique sometimes called balance bagging. Combining these models can lead to better overall performance on the imbalanced task.
Okay, so we've prepped the data meticulously, split it carefully, handled imbalance. We've fine-tuned our LLM using PFFT or other methods. Now, how do we actually know if our model is any good? This brings us to evaluation and monitoring, essentially taking the model's pulse.
Crucial step.
And you mentioned earlier, just looking at simple accuracy often isn't enough, right? Especially with imbalanced data.
Far from it. Accuracy, the percentage of correct predictions, can be incredibly misleading on imbalanced data sets. If 99% of your data is Class A model that just always predicts Class A will have 99% accuracy, but be completely useless for detecting the rare Class B.
Right. So what metrics should we be looking at for LLM fine-tuning, especially for classification tasks?
For classification tasks with LLMs, like sentiment analysis, topic classification, intent recognition, we rely heavily on metrics derived from the confusion matrix. Key ones include precision. This answers the question, of all the times the model predicted positive, how many were actually positive? High precision is important when the cost of a false positive is high.
Like a spam filter wrongly flagging an important email as spam. You want high precision there.
Exactly. Then there's recall, also called sensitivity or true positive rate. This answers, of all the actual positive cases, how many did the model correctly identify? High recall is crucial when the cost of a false negative is high.
Like an LLM screening medical reports for signs of a disease. You really don't want to miss a potential case, so you need high recall, even if it means a few false alarms.
Precisely. Often there's a trade-off between precision and recall, which leads us to the F1 score. This is the harmonic mean of precision and recall, providing a single balanced measure that's particularly useful for evaluating performance on imbalanced datasets. A high F1 score requires both high precision and high recall.
So F1 is often a better single summary than accuracy for imbalance. What else?
AUC ROC, area under the receiver operating characteristic curve, is another very important one. The ROC curve plots the recall, true positive rate, against the false positive rate at various classification thresholds. The AUC is the area under this curve, a value between 0.5, random guessing, and 1.0, perfect classification. It summarizes the model's overall ability to discriminate between the classes across all possible thresholds. Higher AUC is better.
Okay, that covers classification. What about when we're fine-tuning an LLM to predict a continuous value, like generating a numerical score for text quality, or maybe ranking items?
Right, for regression tasks or tasks involving predicting numerical values, we use different metrics. Common ones are mean absolute error, MAE. This is simply the average absolute difference between the model's predicted values and the actual true values.
So if my LLM is predicting house prices based on descriptions, and the MAE is $10,000, it means my predictions are off by $10,000 on average, ignoring direction.
Correct. Another is mean squared error, MSE. This calculates the average of the squared differences between predicted and actual values. By squaring the errors, MSE penalizes larger errors much more heavily than smaller errors. You'd use MSE if large prediction errors are particularly undesirable for your application.
Got it. MAE for average error magnitude, MSE to punish large errors more.
Exactly.
And what about the really generative tasks, like fine-tuning an LLM to write summaries or translate languages or even generate kind or ranking search results? Accuracy, precision, recall don't really apply directly there.
You're right. For natural language generation, NLG, and ranking tasks with LLMs, we have a whole different suite of specialized evaluation metrics.
Like what?
For general language modeling quality, perplexity is often used. It measures how well the language model predicts a sample of text. Lower perplexity is better, indicating the model is more confident and accurate in predicting the sequence of words.
Okay. For translation or summarization?
For tasks involving comparing generated text to one or more human-written reference texts, metrics like BLEU, Bilingual Evaluation Understudy, and ROUGE, Recall-Oriented Understudy for Gisting Evaluation, are very common. BLEU measures the overlap of n-grams, sequences of words, between the generated text and the references, often used in machine translation. It tends to favor precision and literal word matches.
And Rouge?
Rouge is more recall-oriented. It measures overlap based on unigrams, bigrams, or even the longest common subsequent. It's frequently used for evaluating automatic summarization, checking if the key information from the reference summary is present in the generated one. Both BLAU and Rouge have limitations, especially for creative tasks or code generation, where semantic equivalence matters more than exact word overlap, but they are widely used benchmarks.
Right. And for ranking, like if an LLM is ordering search results or product recommendations?
For ranking tasks, metrics like mean average precision, MAP, and normalized discounted cumulative gain, NDCG, are crucial. These evaluate how well the model ranks relevant items. They give higher scores to models that place the most relevant items towards the top of the ranked list, which is exactly what you want in search or recommendations.
And with all this focus on performance, we also need to think about fairness, right? Especially given the bias issues we discussed.
Absolutely critical. Increasingly, evaluation includes specific fairness metrics. These aim to quantify whether the model's predictions or errors are equitable across different demographic groups, defined by attributes like race, gender, age, etc. Examples include statistical parity. Do predictions have similar rates across groups? Equal opportunity is recall similar for each group. And predictive parity is precision similar. Evaluating and mitigating bias is a huge part of responsible LLM deployment.
So many metrics. Beyond just looking at these numbers, how can we visualize what's happening with our LLM's performance during fine-tuning? Are there helpful graphs?
Yes, visualization techniques are incredibly helpful for diagnosing problems. The most fundamental are loss curves. You plot the training loss and the validation loss on the same graph over the training epochs.
And what do these tell us?
They are crucial for detecting overfitting. If you see the training loss continuing to decrease nicely, but the validation loss starts to flatten out, or worse, increase, that's a clear sign your model is overfitting to the training data and losing its ability to generalize. Time to stop training.
The classic divergence. Got it. What else?
For classification tasks, the confusion matrix is invaluable. It's a simple table showing the counts of true positives, true negatives, false positives, and false negatives. It visually helps you identify exactly which classes the LLM is confusing with which other classes. You might see it's great at distinguishing class A from B, but terrible at distinguishing B from C.
Helps pinpoint the weaknesses.
Exactly. And the ROC curve, which we mentioned in relation to AUC, is also a useful visualization. It graphically represents a trade-off between the true positive rate recall and the false positive rate at different thresholds, helping you choose an operating point that balances sensitivity and specificity for your needs.
Okay, visualizations are key. It also sounds like there are a lot of knobs and dials to turn to get optimal performance, things like learning rate, batch size, PEFT parameters. How do we find the best settings?
Yes. That's the art and science of hyperparameter tuning. Default hyperparameters provided in examples or libraries are rarely optimal for your specific dataset and LLM fine-tuning task. Tuning them properly can significantly improve performance and generalization.
What are the key hyperparameters we usually need to tune for LLM fine-tune?
Common ones include the learning rate, how big of a step the model takes when updating weights too high can diverge, too low is slow, batch size, how many training examples are processed before a weight update affects memory, speed, and stability, the number of epochs, how many full passes through the training data related to early stopping, regularization strength, like L1, L2 penalties, dropout rate, and if you're using PFT, the specific PFT parameters like the LoRA rank R or the adapter size of the prompt length.
So how do we find the best combination? Just try random stuff.
Well, manual tuning, educated trial and error, can give you some initial intuition, but it's inefficient. More systematic approaches exist. Grid search exhaustively tries all possible combinations from a predefined set of values for each hyperparameter. It's thorough, but can be computationally very expensive, especially with many hyperparameters or large LLMs.
Yeah, sounds like it could take forever.
Random search is often more efficient. Instead of trying all combinations, it randomly samples a fixed number of combinations from the hyperparameter space.
Yeah.
Surprisingly often, it finds very good or even optimal settings much faster than grid search, especially when only a few hyperparameters truly matter.
Okay, random is better than grid sometimes. Anything smarter?
Yes, Bayesian optimization is a more advanced technique. It uses a probabilistic model, like a Gaussian process, to model the relationship between hyperparameter settings and the resulting model performance, for example, validation F1 score. It then uses this model to intelligently choose the next set of hyperparameters to try, balancing exploration, trying new uncertain areas, and exploitation, focusing on areas that look promising based on past results. It's generally the most sample-efficient method, but more complex to set up.
So lots of options for tuning. Now let's say we've done all this. We've prepped data, fine-tuned, evaluated, tuned hyperparameters. Our LLM looks great on the test set. We deploy it, Is the job done?
Absolutely not. In many ways, the real work is just beginning. Monitoring model performance in production is absolutely crucial and an ongoing process.
Why? Doesn't the test set tell us how it will perform?
The test set gives us a snapshot in time, but the real world is dynamic. Data distributions shift, user behavior changes, new concepts emerge. Once deployed, an LLM's performance can degrade silently over time if you're not watching it closely. Proactive monitoring detects these issues early before they cause major problems.
So what key metrics should we be monitoring in production beyond just the task-specific ones like F1 or MAE?
You definitely need to track operational metrics like latency, how long does the LLM take to
Mhm.
respond, and throughput, how many requests can it handle per second. Also resource utilization, CPU, GPU, memory usage to manage costs. But crucially for performance degradation, you need to monitor metrics related to the data and the predictions themselves.
Like what?
Monitor data quality of the incoming requests. Are you suddenly seeing more missing values, different formatting, unexpected inputs? Monitor the prediction distribution stability. Is the LLM suddenly predicting one class, like negative sentiment, much more or less often than historically? This can be an early sign of drift. And most importantly, you need systems to detect data drift and concept drift directly if possible.
Right, those shifts we talked about earlier. Remind me of the difference again, specifically for LLMs in production.
Sure, data drift, or covariate shift, is when the statistical properties of the input data the LLM is receiving change over time. For example, users start using new vocabulary, asking different types of questions, or the format of input documents changes. The LLM might become less effective because it's seeing inputs it wasn't trained or fine-tuned on.
Okay, the inputs are changing.
Concept drift is when the underlying relationship between the input and the target variable changes over time. The meaning shifts. For our urgent customer support ticket example, maybe a new product launch makes certain previously non-urgent keywords suddenly indicate high urgency. The input text itself might look similar, but what it means in terms of the desired output, urgency, has changed. Concept drift is often harder to detect, but more damaging.
So we need to be alerted when these drifts happen or when performance drops.
Exactly. You need robust alerting systems. These could be simple threshold-based alerts, for example, alert if precision drops below X% for 3 consecutive hours, or more sophisticated anomaly detection models that learn normal patterns and alert on significant deviations in metrics or data distributions.
And how do we safely test updates or new versions of our fine-tuned LLM in production before fully rolling them out?
Good question. Risky to just swap it out. Two common deployment strategies for testing are used. Shadow deployment is very safe. You deploy the new model version alongside the old one. You send a copy of the live production traffic to both models. The old model continues serving user responses, but the new model's predictions are logged and compared offline. This lets you evaluate the new model on real traffic without any user impact.
Clever. See how it does without risk. What's the other way?
A/B testing, or canary releases. Here, you route a small percentage of your live user traffic, say 5%, to the new model version, while the rest, 95%, goes to the old one. You then compare key business or user metrics between the two groups, e.g. click-through rates, task completion rates, user satisfaction scores. If the new model performs better, you gradually increase the traffic percentage until it serves everyone. This gives you direct feedback on real-world impact.
Okay, shadow for offline comparison, A/B for live user impact comparison. And when monitoring does detect performance degradation, what's the plan? How do we respond?
You need a structured response plan. First, investigate the root cause. Don't just blindly retrain. Is the problem really data drift or concept drift? Or is it a data quality issue upstream, maybe a bug in the feature pipeline? Or even an infrastructure problem? Understanding why performance dropped is key.
Right. Diagnose before prescribing. Then what?
Then, take appropriate corrective actions. Often this involves retraining or updating the model. Options include full retraining from scratch, using all available historical data plus the new data, most robust but very expensive and time-consuming for LLMs.
Yeah.
Incremental retraining, where you simply continue training the existing model on only the new data, much faster, but highly prone to catastrophic forgetting.
So incremental is risky for LLMs. What's a better middle ground?
Often, fine-tuning on new data is a good compromise. You take your existing fine-tuned model and further fine-tune it only on the recent data, typically using a very low learning rate, and perhaps techniques like EWC or replay to minimize forgetting the older knowledge. It adapts the model without completely retraining or forgetting everything. You might also use ensemble methods, maybe combining predictions from your older model and a newer model trained on recent data.
Lots of options depending on the situation and after fixing it.
Critically, you must monitor the impact of your corrective actions. Did retraining actually fix the performance degradation? Did it introduce any new problems? Continuous monitoring after the fix is essential to ensure the system is stable and performing as expected. It's a continuous cycle.
It really is a life cycle, not a one-off task.
Yeah.
And just before we wrap up, speaking of optimizing for deployment, we should quickly touch on techniques to make these often massive, fine-tuned models leaner and faster for production environments. Deployment optimization.
Indeed. Two very important techniques are worth a quick mention. First, model quantization.
Quantization, making things into discrete levels.
Essentially, yes. It's the process of reducing the numerical precision of the model's parameters, weights, and/or activations. Instead of using standard 32-bit floating point numbers, you might convert them to lower precision formats like 16-bit floats, 8-bit integers, int8, or even lower.
Why do that?
Lower precision means the model takes up significantly less memory. Example, int8 uses 4x less memory than FP32, and computations can often be performed much faster, especially on hardware that has specialized support for lower precision arithmetic, like many modern CPUs and GPUs, TPUs. This drastically speeds up inference and reduces costs.
Does it hurt accuracy?
It can, slightly. There are different ways to do it. Post-training quantization, PTQ, is the simplest. You train the model normally, then convert the weights afterwards. It's easy, but might have a larger accuracy drop. Quantization-aware training, QAT, simulates the quantization effects during the fine-tuning process itself, allowing the model to adapt and often achieving higher accuracy, closer to the original FP32 model. But it's more complex to implement. The benefit is enabling deployment on resource-constrained devices like smartphones or speeding up inference significantly in the cloud.
Okay, quantization shrinks the numbers. What's the other technique?
Model pruning. This involves removing unimportant parts of the neural network to make it smaller and faster, ideally without significantly impacting its performance.
Removing parts, like what?
You can prune individual weights, setting small magnitude weights to 0, entire neurons, or sometimes even entire layers or attention heads that are found to contribute little to the model's output. This results in a sparse model or a genuinely smaller, dense model.
How do you know which parts are unimportant?
There are various techniques, often based on weight magnitudes or sensitivity analysis. There's also the intriguing lottery ticket hypothesis, which suggests that within a large, randomly initialized network, there exists a smaller subnetwork, the winning ticket, that if trained in isolation from the start, could achieve the same performance as the full network. Pruning aims to find such efficient subnetworks after training.
So pruning physically removes parameters to make the model smaller and faster.
Exactly. Both quantization and pruning are key techniques for optimizing these large, fine-tuned LLMs for efficient real-world deployment.
Outro. Wow. Okay. You have just taken us on a truly comprehensive journey into the world of fine-tuning large language models. We started by really understanding the incredible leverage you get from those massive pre-trained models.
Yeah, recognizing how they lay such a strong foundation of general knowledge for almost any downstream task.
Then we dove headfirst into the sneaky, sometimes frustrating challenges that inevitably pop up. From the inherent data biases baked into the pre-training data and the sheer computational costs.
Right, to those really tricky problems like data distribution shift where the world changes underneath your model, and that frustrating AI memory wipe known as catastrophic forgetting.
But the story definitely didn't end there. We explored a whole range of truly ingenious solutions, from the amazing efficiency gains of PEFT methods like LoRA and adapter layers, which are making fine-tuning these behemoth LLMs much more practical,
To the strategic power of active learning for using human labeling resources much more intelligently, and all those robust techniques for evaluation and continuous monitoring that are essential for keeping these powerful models on track long after they've been deployed.
It really highlights that the true power of these advanced AI models lies not just in their initial massive creation, but in the continuous, intelligent, and often painstaking effort required to understand them, adapt them, and refine them as the world around them and the data they see inevitably shifts.
Absolutely. And as a learner navigating this space, you're now equipped with the knowledge to not only wield these powerful fine-tuning tools, but also to anticipate and hopefully solve some of the real-world complexities and challenges they encounter.
So as we leave you to ponder all this, here's a final thought. Reflecting on your own potential applications or data, what unexpected shifts might you encounter? And how will you adapt your knowledge, perhaps using some of the techniques we discussed today, to keep your own AI models performing at their absolute peak in a constantly changing world?